Are all your friends here? Are we still missing people? Who's missing? Anyone? Lukash is missing. No, he's here. All right. So we'll get started in a minute. Before we start, there are a couple of housekeeping announcements. The first one is that we would like to keep track of attendance at the summer school. Most of the JSALT students who are from out of town, of course, will be here, but there'll be some local students as well. So Radim will circulate a attendance sheet, and when it comes by, you just sign in. If we'll start, are we starting today already? Okay, so we'll start today. The second thing up there is the health and safety forms. So there are a couple of forms we have to fill. These are formalities, but still very important. One of them is that there's a form that talks about safety, fire prevention, and you have to acknowledge that you read it and you'll follow the rules. Another one has to do with health insurance and the personal liability. Those of you who are staying in housing provided by the university, you have to provide some of these forms for that. And then finally, all of you are using the computer network here. So obviously, the school doesn't want you to be running some dark web or other nefarious activities using this network. So again, you have to sign a form that says you'll be responsible users. So these forms are outside. So in the break or any time when you get a chance to go outside, please find your name and sign these forms as well. So the attendance sheet has started going around. Sign that when it comes by you. And then the other two forms, you take care of them outside when you take a break. Right? Okay, so that's as far as housekeeping goes. For the afternoon, we're going to have a lecture. And Ulda, are you going to do any hands-on demo-like things or just play? Okay, all right. So we're going to learn about speaker ID, language ID, things other than the linguistic content of the speech. And for that, I will switch over to this and introduce our lecturer. Are you going to use your own laptop? Okay, so why don't you set that up while I tell people something about you in 2 minutes. So Oldřich Plchot is a researcher here, a senior researcher at BUT. I've known him for many, many years. He used to be the face of their speaker ID, language ID evaluation teams for a number of years, has done some good work in those fields. Also, he's now leading other projects, including one on conversational LLMs, dialogue systems. This is the Horizon 2020 project. And while he was a student, he did some really nice work, and I noticed that he was given a dissertation award called the Josef Hlavka Prize. This was back in 2016, right after his PhD. So without further ado.
Thank you, Sanjeev, very much for a nice introduction. Yes, as you said, I was the face of many of our submissions to the NIST evals in the speaker verification, because I used to go to all of these NIST workshops all the time for many years, but now we have a fresher, younger team who is slowly taking this from us older guys, and we sit down and write projects and try to keep them happy. But nevertheless, I will still be giving you today some introduction to speaker verification and what has been done in the last years. I will try to put it on you on all on the same basis. So even if you don't know almost anything, you can probably get it after today. And after a brief introduction, we will try to overview of what has been happening for last several years and what is still happening in speaker verification. So, okay, I will try to adjust it a little bit here for me. Okay, so the outline of this talk. First, we will just try to think about what are all the applications of extracting the speaker information from the speech, and discuss what is nowadays in fashion, where the technology is being used. And then we will try to go into some basic of speaker verification. We will briefly look at the features, and maybe you will be able to think about what those features can be today rather than what it has been for many years until now. And then we will try to see what was the traditional approach with some GMM-based models versus nowadays what it usually is going down to is a comparison of some speaker embeddings. And then I will just briefly talk about some evaluation and metrics and what are the errors in the speaker ID and so on. And then we will look a little bit more in detail into the generative embedding approach that has been state-of-the-art for many, many years, actually until 2017, roughly, and also quickly look at the generative backends that are usually employed on top of these embeddings, even now on top of the discriminative embeddings, and that would be probabilistic linear discriminant analysis. We can also see that we will also see that this kind of models can be actually trained discriminatively. So we'll also briefly look into that. And then we will slowly but surely transition from these kind of embeddings into discriminative approaches like X vectors. And after that, we will move closer to present and talk about some foundational models, how to utilize them in speaker verification. We'll talk about WAF-LM and some attentive-based backend like MHFA, use of adapters for domain adaptation, and maybe if I'm still able to talk after all of that, we can see how we can leverage large amounts of data that come with just weak labels, not very nicely pre-prepared data, but more like the data that you're about to find somewhere in the wild. So here on this slide, it's huge. I usually show it in this class of speech processing. There are all kinds of speech technologies that actually we are trying to work with in this group, and there is a lot of points highlighted here where speaker information come to mind and where we use it. So utilizing the speaker information out of the speech is not just about building speaker verification systems, but nowadays there has been a huge progress in speech synthesis and actually in making speech synthesis to sound like a speaker that you would like to have. So you can extract a speaker representation from some person you know and make the synthesizer talk like him. Of course, this has some implications, like nowadays a very hot topic of spoofing. So you can actually eventually, with this synthesized voice, attack these biometric systems that that would be designed to verify a target person. Yeah?
Could you please make the microphone a bit louder?
Louder? Oh, okay. Is it better?
I think so.
Okay. I can make it even louder. Okay. So I was talking about spoofing. So the good use of this, of course, you would like to have a nice system talking like a real person, but of course you can misuse this technology very easily. So the spoofing would be this kind of scenario where you would like to break into some speaker verification system. A part of classical speech synthesis, we can also talk about a voice conversion, where you would utilize some target speaker representation to tell the system to on-the-fly convert his voice to this target person. On the other side of the spectrum, we can also look at some speech enhancement technologies, and specifically the cases where we would like to be able to distinguish between several people talking in a recording and try to focus on a particular speaker. Humans, they would do it naturally, where there is a bubble noise around you, and then you would look into one person and try to focus on him. We would do some kind of speaker separation. We would kind of filter out the target speaker out of a mixture of many speakers. So these kind of technologies nowadays also have been progressed quite a bit, also with large foundational models. Juni, I don't know, he's here, he's working on that, so you can talk about it with him as well. And then, of course, we have standard applications, like in the recognition branch here, there is a speaker recognition where we will be building standard speaker identification systems that could be used for personalization, indexing, law enforcement, etc. So this is gonna be the branch that we will be more focusing right now, but I wanted to have this slide here so that you see that extracting speaker information out of the speech is nowadays not at all only about building a speaker verification system, but you will be able to utilize this information in many other areas. And probably I don't have all of the use cases here. One that probably is not here and would be interesting for you in this in the context of the summer school would be, for example, building these speech language models. You can make them speaker aware, so you can be asking the questions who was speaking where, or the model would be better understanding what a single person said, basically being able to parse the conversation better if he is able to distinguish speakers in a conversation. So this slide is about this branch of recognition, basically, and these are the main topics that would be of use of this technology. So on the top of it, the biggest one, of course, is security and defense and forensics. So I think nowadays this is still and probably will be the biggest use of the technology, as we want to search for a suspect in a large amount of audio, waiting somewhere online on the telephone channel and see if the suspect calls or not. Then there are other applications, like more mundane, I would say, like an access control, where you would like to authenticate against the user's voice, transaction authentication. A scenario would be in a bank, they would allow you to do some sort of transactions after being authenticated with your voice. Of course, these two boxes nowadays are a little bit questionable. As I already said, in the last few years, the boom in speech synthesis and voice conversion and its quality have caused very successful attacks against these systems. So the technology, it kind of works very well, but also the other technology that can be misused against this one also works very well, which makes some of the scenarios that few years ago were very feasible and actually saving some time and money for the companies, they are less feasible now because the risk of misuse is being increased. So these two boxes, those will be the cases where the technology is actually a little bit leaving out of the industry, I would say, and being replaced by some other kinds of authentication, usually by a token that you now usually carry with you, and it's some other applications on a mobile phone or biometrics that is much closer to you, like your fingerprint and so on, as this was, of course, not the case many years back, where the smartphones were not so predominant in everybody's possession. So now you can authenticate much more safely with some other biometrics than voice. Voice is a great biometric, by the way, but of course you're giving it away everywhere. Like now I'm speaking, I'm being recorded, it's gonna be put somewhere in YouTube. Somebody will take it, train a model of my voice, and then can authenticate it in my bank. So I probably personally would never allow a bank to authenticate me through the voice. And the other two remaining boxes, they are still very relevant, I would say. The speech data management or personalization, that is something where you don't, you might be in a position to either not allow any attacks like spoofing, or you can actually at least try to defend against it, or the costs of somebody trying to sneak in some data is is not that high as in some access control system. And personalization, you would know it, it's probably a scenario where it is not as sensitive or you don't mind as much. You just want your TV to recognize you and play your channels on YouTube so that when you talk to it, it will just recognize you. All I was talking about is just how to extract this representation from the voice, and we have not yet mentioned that the content of the message can be of importance. So we can, in speaker identification, we can talk about the text-dependent and text-independent systems, where of course the content might serve as some kind of password, so that the recognition systems would know the phrase that you should speak. And these kind of applications, they are used somewhere where you assume a bigger control of the user. So the system knows it, you know it, but also the attacker probably can know it. So it is not inherently much safer, but against the spoofing, but it is definitely better in terms of performance in a scenario where you don't assume much attacks. It can work with very short phrases on a high accuracy. On the other hand, the text-independent systems, I would say these are more widely being used. You don't need to assume that the person would remember anything. He might also not know that he is being recognized somewhere. Like I said, suspect talking to somebody and somebody else listening to the voice and trying to identify him against some embedding or model of this person. And this is the case for the law enforcement all the time, where they try to filter out large amounts of data without people knowing that they are being monitored. So let's quickly look into the basics of speaker ID. I think you came for the JSALT summer school. You must know all about basic stuff like these features, but I wanted to stop here so that you can think about it. For many years, MFCCs basically were the gold standard on the features for speaker verification. These are very simple acoustic features used actually also for speech recognition, language ID, and everywhere. There has been tremendous amount of varieties on these features, but always through many years, all the time, the MFCCs was the baseline, and actually, I think that there is no clear conclusion that this kind of feature or that kind of feature would be the best. So the MFCCs remained kind of a gold standard. So it's based on a short-term Fourier transform of the acoustic signal. Then you would subject it to filtering with mel scale distanced filters, and take a log of it, decorrelate it with the DCT, and you would get some vector of features for every 10 millisecond frame. So you will be getting these sequences of acoustic features and model on top of these. Nowadays, these features, these were of course very well handcrafted. You can see, for example, the mel scale here has been determined by a series of psychoacoustic experiments to reflect how humans hear, what is the sensitivity of their hearing. You can see the higher resolution in the lower frequencies, and when we go higher, the filters would be spaced far apart, which reflects how we hear. And this turned out to be working pretty well. Nowadays, often you train these kind of representations with a convolutional network in these foundational models like WAFLM that we will talk about later. But the truth is that this kind of feature carries most of the information. It is very close to the signal, very close to the spectrum. and it carries very well the anatomical structure of our vocal tract. So we would call these MFCC features acoustic features, and we call them also low-level features because it's just a handcrafted, nice design, very easy to compute, directly obtained from a spectrum for every 10 milliseconds. When we go higher in some cues that we can get from an acoustic signal about the speaker, we have to concentrate on something more complicated and more long-term. So this slide shows some like increasing complexity of the features that would be characterizing individual humans. So as I was talking about, the human vocal tract is kind of unique to each speaker. But of course, what is unique is how they speak, what is their personality. So that would be the prosodics, the rhythm, how fast they would speak, and what volume modulation they would usually use. So these kind of features would be connected to their personality type, or what parents did they have, and perhaps even where they live. And if we go higher enough, even what actually people say, the semantics, the idiolect words that they would be using. Some people say typical words that almost nobody says, or have some phrases that almost nobody else uses, so you can just even read it. You don't need to even hear it, and you would recognize that the person was this kind of person. So these would be social economic features, I would say. You would acquire them later in your life, in your education, by talking to some certain group of people, etc. And of course, the higher you go in this hierarchy, the higher it is, the more difficult it is to kind of quantify these features. And usually you would need much more speech to reliably get some statistics on them, because to get some statistics on pronunciation, semantics, or idiolect, you should hear at least few sentences, not just a few seconds of speech or a single word. Those features would not be there. So here you can think, where can we get such features? Of course, before we were designing specific systems to extract, for example, acoustic prosodic features. But nowadays, the approach is a little less complicated, and we would be letting some large models to kind of extract from the speech what they want. So eventually, we would rely on the fact that our models have seen all of the speech, or a large amount of speech, and if you train them with a given objective, they would figure out what is there to look for. But it's always good to know what to look for and to steer these kind of models in the right direction. So when we talk about speaker recognition, identification, and other tasks in this cluster of recognition, I'm all the time in this talk talking about the verification. But if we are doing a verification on a closed set of speakers, we can turn this very easily into the identification, basically asking whose voice is this, instead of is this target person's voice. There is another application where you can have a mixture of speakers in a single utterance. And this is called diarization, where we are tasked to identify who spoke when. And you will actually have a full lecture about this tomorrow. Federico Landini, who is a graduate of our group here, will have a whole lecture about this, so I will not spend any time more about this. So what would be the two stages that we usually do in a speaker verification in order to verify a person? So first, there is a training phase, or we would say almost also enrollment phase, where we would register a new user. So these slides are a little bit dated, but I kept it like that because this says here that we will be doing some model training on top of the individual speakers. Yes, before we called them models. Now you can imagine that these models would be actually the embedding. So instead of model training, we would here have extracting the embedding of these enrollment speakers. So basically, you ask the speakers to provide a verified sample of their voice, and you will train their personal model or store their personal embedding. And then some new utterance comes. That is the test phase or detection phase, where you would again extract the features and embeddings, or and compare these to your registered models. So you will compare it against your database of enrolled speakers and say which one it verifies against to. Or if this person claims the identity, he would be saying, I am March, and you compare him to the claimed model, and if the scores of the system agrees, you will say, okay, this is a target trial, I'm detecting him, and it's fine. So how that would be usually done? So we need to compute some score, and the score here is basically this two-class hypothesis test. We need to compute a log likelihood ratio between the hypothesis that the signal S came from the speaker model or belongs to the embedding, or versus the likelihood that this signal S did not come from the speaker model. So these two hypotheses, you will need to have some means of evaluating, and then you take a log ratio of them, and that would be your score. And this score you would compare with some threshold. Usually, well, here it is 0, but it can be any threshold that you then analytically set to satisfy your operating needs. And after the comparison, after this thresholding, if the score is larger than the threshold, you say that the target is that the trial is a target trial, meaning that these two segments, they come from the same speaker, or if it is less than threshold, you will reject it, saying they don't belong to the same speaker. So how this was done before? So I was saying that we were training the models. So everything in the old days was modeled with a GMM. So we would be having some universal model that would be modeling all the speech or all the speakers that we would hear, and then we would have the same Gaussian mixture model for a particular speaker, and then we would need to compare some target speaker training data, that is the Gaussian on the top left corner, with some test data. So in this case, you would probably say that that they would not belong together. So how here we would be doing this likelihood ratio? We would ask the model, what is the likelihood of the, I don't know if the mouse would work here, or no, okay. What is the likelihood that these features come from these test features on the top right corner come from the target model versus the likelihood that they would be actually coming from somebody else, meaning they would be coming from a universe of some random speaker, basically the UBM. So we'll be comparing these two likelihoods. So in this case, this will probably not work out, and we would reject this trial. But I would like to have this example here to show you that in this case, we need to deal with the effect of channel variability. That is very important, as the speaker can be recorded over many different channels and can actually look quite different. So we would be first, before doing this comparison of these two likelihoods, we were trying to compensate for this channel. And only now we would be taking this log likelihood ratio. So this process would be called map adaptation or relevance map adaptation in the old days. And before the likelihood comparison, we would first shift these models in the direction of the high intercession variability. So how to identify these directions in the acoustic space that we would like to get rid of? Obviously, we need a lot of training data for that, and we need specifically to observe this target speaker or multiple speakers across many different channels. So the individual Gaussians here would be instances where we recorded the speaker over different acoustic channels, and we would record not one speaker but multiple speakers, and after we see enough of them, we will start seeing some pattern and be able to identify the directions in the acoustic space where there is high variability between the speakers, which is a useful one for us, and the direction that we would like to get rid of, that is the high intercession variability within the speakers across the channels. Okay. So here, I think we have very, very quickly covered how it was done before we actually start using some embeddings and symmetric scorings. And after we are able to represent the utterance by a single vector that we call embedding, we can turn this thing into a symmetric problem. So no longer we will be needing to create these speaker models, and now we can just simply be comparing their embeddings. We can compare the embedding just simply via taking some cosine distance, or here, or often with the I vectors, this was perhaps not enough, as we needed to get rid of the channel, and we would be using some generative backend like probabilistic linear discriminant analysis. And maybe a few more things here. So what did I want to say? So here in this scheme, then, it would not matter which phase are we in, whether the enrollment or the test case, the problem would be really symmetric. Each recording would be, the model of the speaker would be actually the embedding itself. So everything would simplify and be faster, actually. So how to evaluate these kind of systems? So as in any detection system, we would have two kinds of error here. So we would be talking about the miss or false alarms. This is a terminology that is usually used in the law enforcement, or if you are talking about a system that is deployed somewhere in a bank, we would be using false reject and false accept. So the miss is a type of error where we incorrectly reject a target trial, and a false alarm is a type of error where we incorrectly accept a non-target trial. And then the performance of the detection system is measured as the trade-off between these two errors, and of course we can adjust the ratio of this error by moving in this threshold. So eventually we will compute these two quantities, like probability of miss given the threshold and false alarm given the threshold. So simply just taking the number of target trial scores that is smaller or larger than the threshold divided by the total number of target or non-target trials. So here I will just very quickly summarize it graphically. Maybe it will be boring some of you, but let's do it. So we have these scores. They are basically scalar values. So it's actually exactly like this, and we can put a threshold in between them, and then whatever is above this threshold is, the system says, is a target trial. The test speaker is the enrollment speaker or model speaker, or non-target trials that the test speaker is not the enrollment speaker, basically rejecting the hypothesis or the claim. So true accept is a good outcome of this system, where we have a target trial, it's above the threshold, and our system would accept it. True reject, on the other hand, we have a nice non-target trial. It is well below our threshold. The system rejects it as a non-target. Now there is an error. So we actually have a non-target trial, but the score happens to be above the threshold, and we did an error of false accept. And here we have a target trial that is below the threshold, and we missed him. So we said it's not him. So if you would take these scores, sort them into these two heaps of targets and non-targets, and plot their histograms, you would end up with two distributions looking something like this, perhaps. Often they are Gaussian, or they should be, or if they are not, you can try to transform the scores in such a way that they would represent some nicer log likelihood ratio. That process would be called calibration. Usually you would take these scores as a features, and you would train yet another classifier on top of them, training just a scalar and a shift via logistic regression, and transform these scores in this way. So that process would be called calibration. You can also see on this picture that by moving the threshold, you can move the ratio between how many errors of which type your system would be making. So the sweeping of this threshold is actually important, because we would like to see how does it behave in these different operating points. So we would actually like to plot this. So if you take this threshold and compute the miss probability and false alarm probability in every of these points, you can put these into the graphical representation like this. This is called the detection error trade-off. And by decreasing the threshold, of course, you are eventually making no false alarms. So this direction is, as you see in this graph, where the violet arrow is pointing out. And overall, you would like to work on the system in such a way that for all the operating points, the whole curve would be moving towards the origin. It's always good to be looking at these dead curves as you don't only see a single number, but actually different operating points or different applications. And it's easy with this to compare multiple systems in a more complex way. So in this slide, there is just a plot of several different systems that we had on NIST SRE 2010 eval condition, and it sweeps several technologies going all the way back to the relevance map, also with some channel adaptation. Then there is a joint factor analysis and I-vectors. And you can see that how it moves towards the origin and across all operating points is getting better and better. So in this depth curve, you can actually identify some regions that you would like to focus on. So if you're talking to a bank, they would be telling you, okay, we are interested in the region of low false alarm. On the other hand, when you are talking to police guys or to some security service, they would like to focus, on the other hand, low miss probability, as they don't want to miss the suspect in a huge heap of data. And also you would like to look at this point that is called equal error rate, where it is an operating point where the system would be doing the same amount of errors of both types. So it's a nice point that basically summarizes the whole system. It's very good for extracting one number for comparison between the systems, but it's not so great to really tell how the system will perform in a target application. Yeah.
So when you train the model, how do you do the threshold? Is it like an arbitrary value first and then?
So you usually set the threshold afterwards and via the parameters that somebody tells you, like what is the cost of each error. But nowadays you would train the system in a discriminative way, basically optimizing some objective function that is related to the task. It can be an end-to-end system that there you would be directly optimizing the amount of correctly recognized trials, or you can do this via some proxy functions, like actually turn it into a identification function, identification objective, like some multi-class cross-entropy over the set of training speakers, and then extract embedding and compare those, and only set the threshold after some calibration on top of these scores. So during the system training per se, like nowadays when we talk about system training, we usually talk about training an embedding extractor, really. We don't really set the threshold or care about it. So I also wanted to talk a little bit about the detection cost function. That is actually a metric that reflects the operating point and the costs. So these costs, they are very important. So when you're designing this system, you can say, I don't care about the threshold, I don't care about the application, and try to extract as good speaker representation extractor as possible. That is usually should be your goal. But in the very end, when you're deploying the system, you have to be asking what kind of errors it makes and what kind of errors are more important to you. So as an user of the system, you should know this, and there are metrics that will reflect them. So you can assign a cost to each kind of error. You can assign cost, how much does it hurt you when you miss a suspect, or on the other hand, how much does it cost you if you have too many false alarms, spending too much time of an analyst, and quantified it. So that is this detection cost function, and this cost actually identify your operating point. So this triplet of these parameters, cost of miss, cost of false alarm, and a probability that your incoming trial would be a target trial, there's a prior probability, they would define a operating point. So you can see some of these settings you very often see in the papers. So DCF at some BHS would be the it would mean this setting of the operating points. Also, this kind of metric allows you to measure how well the system behaves in the actual environment when you are doing the hard decision eventually. If you set the threshold and you compute the actual amount of misses or false alarms on this set of trials given the threshold T, and then you sweep all of the thresholds and find the best possible number, this minimum. So after you find the minimum, after you find the ideal threshold, and there is a big difference between these numbers, it means that you could have done better in your detection just by simply setting the threshold on your scores correctly. So if this happens, it means that your system is miscalibrated, and so you should either adjust the threshold or you should recalibrate the scores in such a way that the threshold would work so that your final DCF is close to the ideal DCF. Okay, so let's continue. So now we'll have this little historical excursion into something that is already relevant and sometimes still being used as a baseline, and these would be these generative embeddings. We called them I-vectors, or we still call them I-vectors at that time and nowadays. And then we will move on to embeddings that are extracted from a discriminative model. Some particular version of them would be called X-vectors, but let's just call them discriminatively obtained embeddings. Am I now too loud, or is it fine? Fine. Okay, because the mic is a little bit closer, so if I'm shouting too much, just tell me. Okay, so I-vectors, the generative embeddings. The idea behind them would be to transform some utterance into a single dimensional vector. So we would be having, so this model is built on top of the Gaussian mixture models. And the idea here is to transform a large utterance-specific supervector into a small subspace, while it would still retain the most of its variability. So we would have here this equation S is mu plus TW. Mu would be this GMM mean supervector, and T is a low-rank matrix called as an I-vector extractor that spans the amount of dimensions, of course, as this supervector of means, and on the other side, there will be the amount of dimension of how big of an embedding we would like to have, or what the level of the compression would be. And the W is a latent variable, which will be giving you a point in this subspace defined by this low-rank matrix T. And during training of this via EM algorithm in a maximum likelihood fashion, we would not need any labels. So there are no labels whatsoever needed. You just need raw audio. And therefore, this kind of model is relevant not, of course, only to speaker ID, but to anything else, because once you extract these I-vectors, they would be carrying or being designed in such a way that they carry all kinds of variability that has been there in the original space. So this vector W, if we want to get an I-vector out of this model, we would need to do a maximum a posteriori estimate of it and use it then as a low-dimensional fixed-length representation. So, and it would the distribution of this would follow a standard normal distribution. And as it still contains all the variability, we will further need to design a classifier to deal with it. So it is actually a good model already. People were using it in such a way. So if you can take it as an embedding, take cosine distance between the two, and use it as your representation without pretty much anything. Of course, after some sort of normalization that is usual when you are doing the cosine distance scoring. That is the length normalization, basically ensuring that your embeddings are of unit length. But we were designing, at the time when it started, almost exclusively the way of scoring would be to design a generative backends on top of this, where we would take care of the unwanted variability that I was talking about in the previous segment. So here you have it graphically again. S is some utterance specific supervector. Mu is coming from your UBM mean. Then you have this low rank matrix T, the I-vector extractor. Here we would, on this image, we would be extracting actually two-dimensional vectors. So the maximum a posterior estimate of these W1, W2 would then be your I-vector. So if you would set these two dimensions in such a way that your model would maximize the likelihood of the data, that would be your I-vector. So once you get them, once you extract them, you want to model them. So again, it's gonna be a task of identifying what is important variability here and what is a variability that we would like to get rid of. So this probabilistic linear discriminant analysis is a generative model that would decompose the I-vector again into some factors. You will have here some mean over your data and a representation in a subspace, in a speaker space, a channel space, and some residual noise. And we would like to decouple this information and be then able to ask the model to give you a correct comparison between the two I-vectors if they come from the same distribution or not. So now this model has this advantage of being trained basically with a single Gaussian. We no longer have multi-dimensional set of multi-dimensional features, but we have only one for each utterance. And on the other hand, this one Gaussian would be high dimensional, like the dimensionality of the I-vectors would be around 400 to 600, and the subspaces for each variability would be lower, usually like 100 to 200 for speaker space and even less for the channel space. So PLDA, it has not been discovered for speaker verification specifically, but it comes from Face ID. And actually in Face ID, we can have a very nice graphical representation of this equation that we had on the previous slide. So this I-vector can be actually decomposed into these terms as you see it. So we have this mu. It's like some general mean phase that would be this A on the top left corner in the image. Then we would be having a linear combination of the then we would be having the speaker space or space where when we move along the basis of this low-rank matrix V, we would be getting different phases. And the other term is a channel. So by taking the linear combination corresponding to this basis of matrix U, we would be getting phases that look like the same person, but actually come from different channels, like illumination is different, maybe the position is a little bit different. While when we are moving across different speakers, you will see that the face is once looking more like a man, on the other hand it's looking like a woman, or the skin color is different. And then there would be the rest that there is after the decomposition, and that would be the residual vector. So this kind of generative model, we can simplify it we can call it, we can simplify it and interpret it as just a two covariance model where we would be representing our speakers with a Gaussian distribution that comes with a within-class covariance matrix, and our model would know also the variability between the speakers that would be called across-class probability. And we can ask this model to give you a score whether the two speakers come from the same distribution or not, and that is the log likelihood here in the left corner. So we can again do this two hypothesis score, and on the upper side of the log likelihood ratio, we ask the questions whether all of the segments or all of the audio were generated jointly from the same distribution, and below we are asking whether they were independently generated. So this would be this same and different speaker hypothesis. Of course, since it is a generative model, you can also consider not only a maximum posterior estimate of this latent variable, but you can also evaluate some uncertainty, which is a nice property as it is directly built into this model. So because it is mathematically exactly designed to follow, or we assume that it follows such distribution, so we can assign an uncertainty around each I vector, or we have it during the extraction. So instead of just simply evaluating or comparing using just the means, we can integrate across all possible I vectors that would be coming from this particular utterance, and have an estimate that is more precise, especially for a shorter utterance where you don't see enough evidence to really get a good mean estimate. Because as your number of frames really increases, your map point estimate of for this model is quite precise. So considering this modeling with integrating over all possible I vectors would really diminish when you get enough of the audio. So you would then be computing this hypothesis by integrating over all possible I vectors. And here it could help you, of course, because if you have some two utterances that one would be lying somewhere on the boundary, it can improve your performance. Unfortunately, of course, this comes with large computational costs, as you cannot pre-compute the terms as easily. For each utterance, we need to really do these integrations, and it's almost unfeasible to do it in a large scale. Or maybe now it would be feasible, but it certainly is much more costly. The thing is that this model is generative. We can actually turn it into a discriminative problem, and that we would do by taking this scoring formula, which is actually a bilinear form, and the parameters of the PLDA that you have them here listed. I will not just go deep into them, and you can stack them into the matrix of parameters that we would actually optimize via an objective function that is directly relevant to the speaker verification. So we would be actually evaluating individual trials. So this would be kind of an end-to-end system, but already not end-to-end in the sense that we would be going from an audio, but we would be coming from an embedding. But the final objective would be exactly this verification objective. So here you have it. We would be optimizing a logistic regression error function, or we can switch this one to SVM, to the hinge loss function, and by doing so by doing so, we would actually optimize these parameters, and then when we are done, we can then decompose it back into these quantities and score exactly the way as we did when we trained this in a maximum likelihood fashion via EM algorithm. You can, of course, also, and what we did, we can regularize this model during training, so you can do some simple L2 regularization, or you can try to say, okay, I have trained this model in a discriminative way, in a generative way, sorry, and I would like to discriminatively kind of fine-tune it or continue training and see if I can squeeze out something more out of it. So you can put this regularizer to work like that it would draw the model towards the original parameters. And so this was a very, very, very brief just mention of this generative backend that we would be using for obtaining the scores with these embeddings. They are still being used even on top of the X vectors, but less often so as we did it with the I vectors. So here on this slide, I already have something that would go into the direction of using pre-trained models, but still this was done in the I vector scheme. So as I already was saying, the whole I vector is built on top of the GMM UBM model, collecting the statistics and compressing them into the I vector space and then comparing the I vectors. So here in this case, the Gaussian mixture model, when you get the test utterance, it would be assigning you the frames into the individual Gaussians, basically clustering the acoustic space. But already at the time of this publication, or even before, like a few years before, we had models for speech recognition that were trained discriminatively to classify xenons, acoustic units for speech recognition. And actually, this is a very good model to serve as a model to assign the frames into acoustic units. So we can switch this function from a GMM UBM model and assign these occupation counts not by a GMM but by a DNN, and train the model and then continue in the I vector framework in the same way. This turned out to be actually quite good, and more importantly, it was complementary into a purely acoustic-based system or GMM-based system. So we often got an improvement with a fusion of these two approaches. But what we could also do, and what is the easiest way, and eventually we ended up using it in that way, is that you can take some inner representations from this pre-trained model. So this large neural network that was doing the acoustic unit classification into the xenons, it contained a bottleneck layer to effectively compress the information within it. And these representations were like 80-dimensional. So it is already a nice acoustic feature, I would say, or a usual way, because when we were working with MFCCs and building I vectors models, we would be stacking like MFCC with its delta and double deltas, effectively using something like 60-dimensional feature vector every 10 milliseconds. So here, from this network, if we extracted this bottleneck layer, we would be getting something like 80 dimensions. So it's completely feasible. So you could obtain then pretty much similar results as with this DNN-based alignment. You could obtain it with just using this bottleneck features as a standard acoustic vector and building up a normal I vector-based systems. Or if you even want to do the fusion, already in the feature space, we concatenated the MFCCs with these bottleneck representations, and again, trained I vector systems, and it would be an acoustic features that would resemble both. A nice acoustic clustering of DNN with a strong acoustic features of MFCCs or strong acoustic information, because this DNN network that is actually trained to recognize phonemes, synonyms, it is actually detrimental for it to retain the speaker information. But it is important to be able to extract the statistics on how things are being said, and definitely these two features were complementary. And when you concatenated them, you got very nice results. So this approach of concatenating acoustic MFCCs with these DNN bottleneck features was for quite some time the state-of-the-art approach to speaker ID. And it was one of the, I would say, it was not really a foundational model, but as this network was not as huge as you now have it, it was trained in a supervised way, but in a way it was a pre-trained model that was turned into a nice feature extractor for a completely different task that it was trained before.
Sorry, one question. I was just wondering if probably I missed something, but the I vectors depend, are they fixed size vectors? Or
Yes.
they depend on the uterus?
They are fixed size.
Okay, so what happens, then the I vectors depend on the uterus length? Somehow, like if you have shorter uteruses, then you have bad representation?
Your I vector is, because it's a maximum a posteriori estimate of the latent variable, and you just collect the statistics not so accurately, or basically you don't collect enough statistics, so then your mean estimate is not as precise. So that I vector is just a mean of some posterior distribution, and you need enough evidence to estimate it. So if you just have very few frames, your I vector is a bad estimate, and that's it. Okay, so here we already would be moving into end-to-end systems. So end-to-end systems in its true design should be that you go from the audio till the decision that is exactly your actual decision. There is no need to extract any embedding from before and from within, and then to model it in a different way. So that is the true end-to-end system. And one of the first here was this system from Google, this end-to-end text-dependent speaker verification, where they just used a DNN or last output of an LSTM to obtain representations that would just be subjected to some cosine similarity, obtaining a score, and training a logistic regression on top of it. So, and here in this scheme, you would have always a pair, like an evaluation utterance and one or several enrollment utterances. You might be wondering, DNN here, it would be giving you a sequence of frames, but actually not here. This was done on a fixed amount of frames, and they would just put everything always in it, and so that they would just have one input, one output, so that it worked. And LSTM, they would be putting a sequence, but they would be always just getting the last output, and it was a short utterance. So the LSTM kind of worked nicely. And it was a first true DNN system, end-to-end system. It worked pretty nicely also it worked nicely because these guys, they had hundreds of thousands of speakers, and they trained on a phrase, something like "Okay, Google," which is very short, and it is also combining this text dependency of how this particular phrase "Okay, Google" is being said by particular speakers. So this design worked for them, and was actually one of the first to be considered truly end-to-end. And then there was this approach by Daniel Snyder and Dan Povey, where they, in 2016, where they took some network in a network architecture. They actually did some pooling and were scoring in the end via a end-to-end loss. And still here they had this concept of inputting, enroll, and test utterances, first one, then the second one, and then they would be comparing those. So for every evaluation you have to go through this network twice. This worked at the time. It needed a much larger amount of data to be trained than was available to the community, as this was presented on some private data of, at that time, I think it was also around 100,000 or maybe even 150,000 speakers, which is much larger. At the time we were using something like 10,000 speakers at the most, and when we tried to, or even the authors, they tried to replicate it in this setting, so it was not particularly beating the iVectors at the time, but it was also a nice attempt to do a speaker ID in an end-to-end fashion, and already having here these, yes? This was a binary classification task because you had to propagate both enrollment and utterance once, and then use these quantities S and B also to do the scoring, to obtain the final score. So the journey to the true X vectors have continued. So actually, here it is something that is already quite close to the concept of X vectors. So we were in a team with Patrick, Kenny, and Cream, and for speaker verification, NIST speaker verification, and then there was a workshop in, I think this was, SLT in San Diego somewhere, yes, where we had this system that was called speaker classifier network, and basically the idea there would be to train a speaker identification system on a set of training speakers. We would know the labels. We would be training just with a classical multi-class cross entropy here, but in the middle of the network we would be obtaining yet another representation of these I-vectors that would be somehow transformed, and we were using them as an input to NPLDA. But the thing is that this concept of decoupling this problem into first training in a standard multi-class cross-entropy obtained some representation that is subject to this task, and then use it for actually speaker verification. It started the X vectors, because when we were at that workshop, we had a talk with Dan Snyder and Patrick Kenny at the table, and because Daniel Snyder was doing this system where he was struggling with it, And he said, okay, you can just replace this complicated binary loss and the fact that you always need to compose the trials during the training, just with this, train over a set of known training speaker with a simple multi-class cross-entropy, and then deal with the objective later on top of the embeddings. So he did that. What they used for as a DNN network here was a well-known at the time neural network. Is like 1D convolution layer called TDNN, time-delayed neural network. It was a concept that was already known back then for a long time. Alex Weibel, I think, already in 80s or 89, introduced it for phoneme recognition, and here they leverage it for this task of extracting the embedding. So what they did is they took this TDNN, and at some point in it they put a statistics pooling layer. So this is a point where we would be taking the mean and standard deviation of the frame-wise layer representations, and from this point on in the network, we would continue segment-wise. So we would be subjecting this representation then by transformation with the two fully connected linear layers, and the objective here would be exactly the same as we did then with the I-vectors. It would be training on the set of training speakers with a multi-class cross-entropy. And these representations just before the last layer, they would be called X-vectors. And this performed pretty well at the time. Eventually, this TDNN network was replaced by ResNet, but the concept remained exactly the same. And these concepts with the ResNet now, not the TDNN, it does give you still state-of-the-art results. So here there is just a little comparison of how the technology has developed during the time, and you can see that it was dropping a lot every single time that there came the shift. So the drop from I-vectors to X-vectors is still very, very significant. Nowadays, I think that we are again in a little bit of a plateau, and it's hard to improve the results. But perhaps with the large pre-trained models, there has been yet another step, but not as pronounced as the step from the I-vectors to X-vectors. So these representations nowadays, they would be considered state-of-the-art and are being used very often. So as I told, when the TDNN was replaced by a ResNet, it is a convolutional network that is very known again from the image recognition, and we would be following the same way of putting a pooling layer somewhere inside of it, and not going directly to the very end, as we are dealing with a variable sequence length. So not a picture like here where we could actually always, for a picture of a certain dimensionality, we can always go to the very end if we design the architecture correctly, but with speech, with a variable length, we need to somewhere put this frame pooling layer to obtain the fixed representation and continue segment-wise from there. The problem with the ResNet is that without any special treatment, without some positional encoding, it is looking at the features in such a way that it does not care so much about their locality. So it would be perhaps pretty happy to tell you that the picture on the right is a face because it would correctly identify a feature of an eye, eyebrow, mouth, nose, and so on. But it would not, if it would not be very deep, it would not look deep enough to capture the distances or the distance properties between these features. So he would eventually tell you, okay, this is a face, because it just could not distinguish that these very nice features that it has seen in the picture, they are just completely messed up and arranged in an improper way. So that's where these transformer models come, and they employ the mechanism that is called attention, which actually looks over the whole utterance and trying to determine the relation of all of the speakers to each others and capture it and use it. So I think that yesterday you already had a talk about transformers, so I will not spend much time on it, but maybe just very briefly. It came from the NLP world with this BERT model that was trained in this mask-based fashion to do several tasks at the same time, like named entity recognition, question answering, and so on. And this way you got a pre-trained model that is actually able to somehow understand the structure of the language. All of these tasks during the training could be composed in a unsupervised or self-supervised way out of the data itself, because you were just masking the known things from the data. And then when you used it, you switched the tasks and fine-tuned it for yet another thing, and it started to work very nicely. So in a speech world, we would use a similar concept, just the inputs here would not be the sequences of sentences or text, but an audio. And also in the case of this particular model here, WaffleLM, it would be a mixture of the audio with the noise. We would train it with this mask-based loss, trying to predict actually the original denoised or original clean version of the utterance. So I think Peter yesterday explained how these transformers are being trained. So this, I will just tell that this one, the WaffleLM, is tailored perhaps for speaker recognition diarization. It was designed by Microsoft, and it jointly learns this masked speech prediction and denoising. And of course, all of this can be done in a self-supervised way. And when this is ready, the system can basically very nicely cluster the speech into these acoustic units on its outputs. These acoustic units in the very beginning of the training of the model are obtained by some simple k-nearest neighbor clustering of some kind of acoustic feature. So here we would, for example, use MFCC. It does not really matter as long as we see enough speech representations, cluster it into the units. We don't really need to assign them any specific particular meaning or label, but we just set them in the beginning by the clustering algorithm, and then train the model to cluster all the speech you can see into these units. And it turns out to be a very good approach to come up with a model that is very well suited to serve as a powerful feature extractor. And these models, they have shown a lot of use across the speech tasks. So they they, as I said, they employ the positional encoding and are very effective to identify important features. And they take into the account almost also the long-term dependencies. They, by clustering into these acoustic units, they provide an efficient discretization, and they are deep. They have inner representations that are extracted for every frame, and they can serve as a good frame-wise feature extraction. And once you train them, they provide a very good starting point for all kinds of fine-tuning, as these models are millions, hundreds of millions of parameters, and they were not exposed to any particular task, and they are kind of like a nice brain to be fine-tuned for whatever you want. Okay, so I will probably skip this one. So we, of course, try to figure out how to use it for speaker verification. One obvious choice for you would be, okay, let's just take the frame-wise representation out of this model and build something like an X vector on top of it. So people actually did that. So on the left part of this, you have schematics of some pre-trained model, like WaffleM, or it could be Hubert or Wave2Vec. The concept is the same. People would be taking the last layer out of this model and treat it as just standard acoustic features and be putting a ResNet or an EKAPA-TDNN model on top of this and train it like a X-vector extractor. They would either be keeping the model fixed, or maybe I think they would also try to fine-tune both of these at the same time. But the fact that they were just misusing this very huge model as a simple feature extractor and utilizing only the output of it, where the output is actually designed to be clustering into some discrete acoustic units, might not be very well suited for speaker verification. They had to do a lot of work, adding a lot of parameters on top of it and train all of this. So it is known that inside of these large models, the representation, they actually carry different information in the different levels of this model. So the closer you have your layer to the input, the more it is closer to these acoustic features I was talking about, like MFCCs. Actually, this CNN encoder is something that is basically learning some filters and subsamples the raw acoustic waveform and extract something that could, you can say, resembles something like acoustic features like MFCC or melt filter banks or whatever it likes to learn. And the representations that they are close to this, they carry most of the speaker information, while the representation on the very top, they are very nice for building a ASR system, and they carry more information about the acoustic units the frames should belong to, and basically representing what and how the speaker is saying. So the natural idea here would be, okay, we would like to utilize all kinds of information because we said it is important to take into account these acoustic features as they represent the vocal tract very well, but it is also good to look how the person talks or what kind of words he is using all the time. So it is just natural to extract the information from all of the levels of this pre-trained model at the same time, which is what we did, and we put some also some trainable weight on each of those representations, and passed this information into an attentive pooling, multi-head pooling mechanism, where we turned the frame level information into the fixed length representation. Doing this for multiple heads can allow the model to be looking in parallel on a different types of features at the same time, and it also would resemble a little bit the effect of what we were seeing in the DNN-based approach, where we were assigning the acoustic classes with the DNN. And so I think maybe I can also say here that we have, okay, I think I would leave it at here, because I would get confused here and confuse also you. Yes?
How do you manage to condition the linear layer to, like, from what I understand, the value should only contain speaker information, which is the
Yes.
purple branch, right? But how in practice does it work? How do we manage to do this conditioning?
How do we
manage to condition the multi-head factorized attention so that the values contain the speaker information but the keys not?
Just because we decouple it into these independent things, because we once take these inner representations into the transformation for the values and independently into the keys, and train it with the one objective at the same time and therefore for the keys you would have also the multi-head attention, so you can look at the different things at the same time. So we use all of them. I probably at this presentation don't have a picture of how the weights end up, but they would be more pronounced in the first few layers. Then there would be a plateau, and then the layers would again increase in the very top. So that would suggest that it is at the same time looking mostly at the beginning and then at the end of the network. Okay. I have this picture from Juni's presentation here. It's a variation on this MHFA that he calls context-aware MHFA. That is the latest variation of it, where he would also group the queries with a local context, and it gives him a little bit of a boost in a performance. And this has been published in the last ICAP, so I put it here as this is the last incarnation of the MHFA, but the concept would be still the same and pretty similar, just that the values here would be coming with a frame context.
Queries are like latent variables which are identified during the learning itself.
Excuse me?
The queries,
Yeah, they are identified during the learning.
It's quite different in some ways.
Yeah. So I have here a few numbers. So what you can do is, of course, take this backend, put it on a frozen model, and treat it as it is, as a feature extractor, and don't let it being retrained. And still, this kind of backend nicely and effectively extracts the information for the target task that you want. This is actually the concept that has been introduced by this superb benchmark, and we would do this when we would like to compare individual pre-trained models, how well they kind of extract the information on their own without any specific training. But always when we have relatively enough training data, or not even that, always when you want to get the best performance for the target task, it was for us beneficial to let the pre-trained models to be fine-tuned together with the MHFA. So we would let also the transfer model parameters to be retrained. Of course, during the retraining, you would need to be careful and assign different kinds of learning rates, different values of learning rates for the part with the pre-trained models and for the MHFA parameters. So these results, they just show the performance of these backends compared to kind of a strong classifier like Ecapatidian, and that would be put on top of the last layer of the pre-trained model. And here it was evaluated on speaker verification, emotion recognition, deepfake detection. So it's actually quite a universal concept, not only being used in speaker verification, but you can utilize it for anything that you have labels for. For example, instead of speakers in the softmax, you can put languages and have a language ID system out of it. These are the results with the speaker ID when the model is actually being fine-tuned, the WAFLM model, together with the MHFA. And I think that these results are pretty state-of-the-art right now. You can, in the beginning of the table, also see the performance of large ResNets, which they are pretty good. Like if we look at this voxelab 1E or H, these would be like in the same ballpark still as the results on top of the WAFLM. So still good, but it's just a completely different system. And actually, to train this WAFLM-based system with MHFA, it takes less epochs and less compute time than to train the ResNet 293 from scratch. I think the best results here, they contain some sort of quality measures. This is this QMF. So you can say it's better, but I don't know if this ResNet 293 actually contains this. Probably not. So the fair comparison would be without it, and we would see that we are in the same ballpark. Maybe the MHFA slightly beats it sometimes, but not by much. And I would say the results are very comparable. But anyway, it's a completely different concept, and it's nice that it works very nicely.
Sorry, you just mentioned that you need less resources to train the model that combines WebLM with MH.
Yeah.
But considering the pre-training,
Excuse me?
considering the pre-training, or without considering the pre-training of the WebLM.
So WAFLM, we take it as a pre-trained model. Okay. So it's pre-trained on LibreLite data, tens of thousands of hours of data, and then we move it into this domain of voxelab. And put MHFA backend on top of it and already fine-tune it for the target task. You can. We have also tried to train it from scratch, but we have not really on the target data. But this hasn't, at least on this amount of data that we had available and the amount of compute, it did not improve the results much. So the fine-tuning on this data was enough. And when I talk about fine-tuning, I always mean it is with respect to the target application. What you can also do here with these models is to do some try to move them to a new domain or to a domain with scarce training data, and you would like to be able to actually get something out of it. Because it's hard to train such amount of parameters on a very small amount of data. So you can have this concept of adapters where you can freeze these large pre-trained models and only input some trainable parameters inside of the model. Like, for example, around these feed-forward layers, you would attach some bottleneck that would be then basically providing you yet another representation that you would add to the original representation that is there constant and frozen. And these parameters, they are much less than the original pre-trained model. So you would, by fine-tuning in the target domain, you would be taking already, let's say, the model that has been fine-tuned for the target task in a voxel app data that is representing the task, but a different domain. And then you would move to yet another domain. Like, let's say here we were using Chinese CLSP data with much less speakers and much less hours of speech, and only continue fine-tuning with the model frozen, but adding few additional parameters of these adapters, and then evaluating it. So, and these adapters, they can be trained for multiple domains at the same time. You can have them stored in a memory, and when you identify the domain on the fly, you can just switch to the domain of your choice. So it's an interesting concept if you want to do some on-the-fly domain adaptation, especially if the domains do not have enough training data, or if you just simply want to have one universal model, have it in the memory, and then have a data bank of multiple domains that you can on the fly switch on. So we showed here that we are getting perhaps to a similar performance as with the adapters as with the full fine-tuning, and we can use like 20% or even less than 20, actually around 10% of the parameters on top of the frozen model and achieve a very good performance with them. I think let's perhaps skip this, but it's a table that is just showing you how well it performs when doing this kind of domain adaptation. This is this experiment in the CLSP, and we managed to be actually able to use these huge models in this kind of scenario where we have a small amount of training data thanks to these adapters. Because if we just took this without any fine-tuning for the target task in the voxel lab domain, we would be achieving much worse numbers than here. So here we effectively kind of combine these two data by fine-tuning subsequently on both of them. but we wanted to more kind of present this scenario of a possible domain adaptation. Of course, if you would be designing just a specific system for the C and CLSP particularly, you could just probably concatenate the two training data sets and try to optimize until you get even better numbers than these. But that would not be so practical, because then there would come yet another data set that is different, and you would need to do this yet again. So if you're interested in such a scenario, you can take a look into the paper we had in ICASP 23. This publication, or this experiments, this reference is about actually your question, Fernando, about if it is feasible, or if it is better to self-pre-train the model on top of the target data. And we can also ask the question whether it is not better just to directly start from a randomly initialized model and train it directly for the target task. Like we can load a WFLM architecture, and instead of starting to train with the must-based loss, we can directly go for the speaker ID loss. But it actually turned out that it is beneficial to first pre-train the model in this must-based loss to teach it how to cluster the acoustic space very well, and only then do the fine-tuning for the target task. Okay, so there is a little summary about the SSL models for speaker verification. Definitely, it's an interesting direction to look at, not only just indefinitely increase the amount of parameters in the ResNet and multiply the amount of training data. For sure, if you have enough of such data and large ResNet and lots of compute power, you will be doing well. So this approach of standard X vector with the ResNet, it's still good. But also, if you just want to fine-tune with a slightly less amount of data and utilize a nicely pre-trained model and obtain these models in a more cheaper way, this is a very interesting way to go. And as you have all kinds of models readily available for you, and you can train such a embedding extractor almost 10 times faster than the ResNet from scratch. And I have one more segment to go. I think let's do it very quickly. This is a little bit different problem that we were dealing with so far, and that's the problem of weakly labeled data. So all of this assumed that we would be getting, somebody would give you a nicely labeled data where we would assume a single speaker in an utterance, and we would just simply construct a nicely understandable model that would directly optimize our final task. But in the wild, there is a lots of data that are loosely labeled or weakly labeled, and there can be multiple speakers present in it, but also we know that some information about the speaker. So we know who is talking there, or we at least know some of the people who are talking there, but we just do not know when. So you can, of course, design a system to deal with this, and the original VoxelLab data that have not been yet cut in this specifically designed pipeline into the segments that we kind of trust, they are there, and it's worth to look at them and see if we can utilize them for training. So this is actually work that we started with Láďa and Temos a few years back, and now Sarah, who is here, she has continued in it, and we have submitted yet another publication about it, so you can ask her for more details. But the thing is that all of us in speaker verification for all of us, the VoxelLab dataset is kind of a gold standard, but it's good to still remember how the data was collected. This collection algorithm is a little bit, I would not say flawed, but it's very restrictive, and it puts some sort of implications into the data. So there was a face recognizer used during the recognition, so the persons had to be facing the camera. They had to be speaking in such a way that their lips are being seen, and only then, when all of the conditions of the quality were met, only then the segments were considered to be used for the VoxelLab data. So this kind of extracts the data that are inherently easier than some of the data you might be facing in the wild. The pipeline was rejecting lots of the segments, mostly, of course, when the celebrity's face did not appear on the camera well, and the whole pipeline maximized the precision of the segments in the expense of the recall. And of course, the whole thing is not applicable to other modalities where you don't have the video, like telephone conversations or radio broadcasts, etc. So we have designed a system to try to leverage this kind of data in a, I would say, self-supervised way. So we can ask here the question if we can detect the segments where the celebrities are talking without this visual component or any other pre-trained model, and we would be knowing only the weak labels. Like we would only know which celebrities appear in the recording, but we don't know when they are talking. And we are not going to run any supervised diarization system that would be helping us here to do so. And we also might know that there are other people appearing in the recordings, and for which we don't even have a weak label, but we do not assume any other information about them. So the pipeline that I will just very loosely speak about it here that we did is that we train the system in 2 stages. So first, we perform some very basic clustering, a diarization without any pre-trained models whatsoever, and then we assume the clusters clusters we are getting from this are of high purity and of a low speaker coverage. And then we trained a network with an aggregation function over all of these clusters. So we modify the objective function, and eventually we filter the chunks that our system is assigning only to the celebrities for which we have the weak labels. And after this, we rerun the system once again and retrain it in a standard way, as if these segments being identified were having proper labels. And doing so, we achieved results in the same ballpark as at the time with standard ResNet on these supervised segments coming out of the VoxelLab pipeline. So this actually is an interesting result, because if you just improve a little bit these results, you will definitely get towards the same performance, and you don't need to assume so much things about the data, or you don't need to have such a restrictive pipeline, throwing away a lot of speech, throwing away the sources without the video modality, etc., etc. And still you get a reasonable or comparable speaker embedding extractor that just does not have such high requirements of the training data labeling as you had before. So the training data being nowadays often one of the most expensive part of the system training to obtain them. This can be an interesting way to get them and to utilize them if you don't have other training data. Okay, so that's the end, and I will just summarize the whole second part of the talk. I just want to say that the pre-trained models are very nice way of dealing with the problem, especially if we don't have enough labeled training data. We can utilize the self-supervised paradigm to leverage the totally unlabeled data to pre-train the model and then fine-tune it for a target application, which much less training data needed, and also less time if somebody does this pre-training for you. And if you have plenty of training labeled data, still the ResNet style-based embedding extractors, they perform very well. You can obtain state-of-the-art results with a pretty simple architecture, I would say, just by extracting these embeddings and then mostly taking cosine distance scoring with them, not even considering models like PLDA and so on. So I think that's it. I will stop here. If you have more questions, we can discuss it. And thank you for your attention.
Well, I have one more question, which is like just wondering if what is your guess like with these SSL models, because those models are 4 years old and there are many models, you know, that I've been playing with this Web2Expert model. So there is this order of magnitude increase in number of hours of training data. Would you believe that this increasing data will provide us some increase in performance?
I believe so, but depends in which tasks. It's hard to see in Speaker ID and specifically in the voxel app. It's such a easy and clean data of one domain that it is the results are being now almost too good to be true. If you go into the wild, you will get much differential error rates than these. Certainly, what can help is to have these systems trained on a multilingual corpora, and then we would definitely love to see some multilingual large set like a voxel app. Voxel app contains some non-English data, but it's mostly English. But I think that having these pre-trained models focusing on multilingual data can give you some boost. And on the other hand, I still think that probably training on clean data is still fine to do, as really, I think the problems of channels, you should deal with it in your target application and target domain perhaps later, as I think the objective should be to really nicely understand the speech, how to cluster it, how to discretize it, and some noise. It's so variable that you will most likely not cover it in your pre-trained scenario that often is kind of detached of your target application, unless you really are in a position to get hundreds of thousands of data of your particular domain. Then if you're in this position, then of course it might be good to start training everything from scratch on this data. But I don't know how to answer this, because we just are not in a position to do so many experiments like that.
Maybe one side of the thing
Just that we have seen that this pre-training gives you good initialized model, but maybe it's not, we are not that sure how important it is to use these huge amounts of data, especially for speaker ID. So the one insight was that when we would, for example, use WAF-LM, which is trained on tens of thousands of hours of data, but if we take just the VoxLab data set itself and we do the same pre-training just on Vox, if we train, supervised train on VoxLab, we get certain performance. We get much better performance if we pre-train the model in unsupervised way, but on the same data. It's still on VoxLab, and we would get about the same performance as if we would take the WAF-LM, which is pre-trained on a huge amount of data, and then supervised fine-tune it to the data. Again, I guess that these experiments were just on some data sets, so I shouldn't generalize, but this is it. So basically, it's questionable whether we would benefit from having huge amounts of pre-training data. It looks like that just the way how the SSL models pre-train things is somehow gives you very good initialization, but at least for speaker ID, maybe it is enough to use the data sets that we have right now, and we don't need that much data for pre-training.
Okay. Of course.
So like, if you think about the way speaker ID, speaker recognition was framed in the past, right? You would have an enrollment recording, which could be several seconds to several minutes, and you'd have a test recording, which could be, well, okay, we did look at short segments like 30 seconds, and even 10 seconds or 5 seconds, right? But, and you'd think if you looked at those results that it's a solved problem. That with 30 seconds of enrollment, 30 seconds of test, you can pretty much nail it, right? And still, if you think of speaker diarization, which is sort of a different variation of the same problem, right? You have multiple people talking in a room, and we're terrible at it, even today. So where is the gap? Is it that we need a different model, or if I push the extreme, I say I'll give you 10 seconds of enrollment and 1 second of test recordings. I mean, speaker ID is still pretty bad at that setting, right? So I guess, so what do we need to solve that last bit of the problem? If you want to call it the last bit. I think it's just the tip of the iceberg, but.
It's hard to say. The clustering itself, it's a completely different class.
Yeah.
It's a completely different problem than a verification only.
Yeah.
So it's much more complicated.
Yeah. By the way, the idea is not to put Olda on the spot. There are many people in this room who work on diarization. So anyone else has any thoughts?
Maybe I'd say that the big difference is the lack of speaker turn that's different in the two tasks. Like in recognition, there is only one speaker, and so it's task easier. And diarization, there is also the fact that the confusion part of like mismatching one speaker to two speakers that are talking together, and so yeah, there's this parameter to which makes, I think, task harder, even though they are pretty similar in appearances, I guess.
Why do you say that the diarization is doing terribly? I mean, we have almost perfect diarization systems these days. So no, I mean, seriously, the systems are not that bad. I mean, of course, if you look at the diarization error, there would be on some data sets you would get something like 13% or something like that. But if you try to analyze where the systems makes errors, the most of the errors comes from overlapped speech parts. So maybe this is the problem. I mean, we just cannot deal that well with overlap speech, and saying that if they are speaking 3 speakers at the same time, that we cannot all that confidently say that there are these 3 speakers speaking at the same time. Do we really need to know that? I mean, this is actually we are asking diarization to do something that us as humans, we cannot do really all that well. And then, of course, there is always non-zero diarization error, but it is also often because of the way the data sets are labeled. I mean, diarization is not well-defined problem. That's the first thing. Zach?
Well, so let me push back and say, imagine it's a 3 or 4 person conversation, right? And somebody says something and one person says yes, the other one says no. Can you say who said yes and who said no?
I would say so. I mean, I don't think that it is such that the best diarization systems that we have right now are performing fairly well, and most of the errors comes from the.
No, not from one word, Lukash. I don't believe it.
Well, okay, we will show you our diarization system.
Okay, especially if you have like people with similar ages and demographics in the room. It's pretty hard. I mean, and then on top of that, if you say, if somebody is speaking and the other person says no in an overlapped way, then it's completely hopeless. But at the same time, if you're in the room, even with your eyes closed, you can say who said it. So it's not like you're relying on your eyes or anything. So I still think speaker ID and diarization. It's weird. What is happening? No, it's some feedback. I don't know what it is, but it's all right. Oh, I'm standing right below the speaker. Maybe that's why. A little better. This case of Trayvon Martin, who was killed by this guy Zimmerman. And there was forensic evidence of somebody calling out for help. And it was recorded on a 911 call, but experts couldn't agree who was calling for help, whether it was Trayvon or Zimmerman. So speaker ID, I would say, is still not solved, even for here. By the way, don't ever compare with humans, because we've shown.
Thank you very much. And I hope that you will have a nice summer school, and I will be mostly here through the whole summer. So we can discuss this slowly somewhere in the kitchen with coffee if you want to, and where I'm less stressed and and can be a little bit slower. So thanks a lot again.